And we're going to start with the PowerPoint. I know, I'm impressed too. All right, reaction types. Reaction types. I know we talked, how far did we get on Tuesday? Did we go through, I think we just got through single replacement, didn't we? Or no, combination? I think we just went, we got through single and double. Oh, I think just the general form. Okay, we're going to go through them in detail. We're going to start with combination reactions. There's a couple right there. Combination, the general form of a combination reaction is going to be when you take two smaller things, like in this reaction down here with the Haber process, nitrogen gas, hydrogen gas makes ammonia gas, and that's a combination reaction. So you take two smaller things and you make one larger thing out of it. Same thing here. This is basically what the reaction above the pictures are. This is a magnesium ribbon. When you ignite a magnesium ribbon, it starts to burn, and magnesium, you can't put it out once it starts to burn. It's also a very bright light that makes, it's such a bright light that if you look at the flame directly, you can burn your cornea. So magnesium is interesting. You can even, magnesium is what's in the road flares. Have you ever seen a road flare? You know, you have a car accident, it's raining and stuff outside, you see a road flare, you scratch it on the ground, you put it down. Even if it's pouring rain, it stays lit. We found this out when I was in my gen chem class, when I was in grad, and we went, oh, that doesn't go out. So we said, well, let's try something at Lake Mary. I went to NNU, so we went out to Lake Mary, drove out to Lake Mary, took all those road flares, scratched it on the ground, started to light it up, threw it in Lake Mary. Don't try this at home, it's very bad for the environment. Threw it in Lake Mary, hit the water, went all down on the Lake Mary, and it continued to burn. We tried a controlled experiment. We lit one just in the regular air, and the one that was in the water only went out a few seconds before the one that was in the air. So that's why they make those road flares out of magnesium with magnesium wick, because they never go out even in pouring rain. Now, there are sometimes detrimental effects to this idea. Magnesium is also a very strong metal. It's also a very light metal in comparison to other metals. And Volkswagen found this out, and they started to make their automobile engine blocks out of magnesium instead of iron, because magnesium was so much lighter, so much stronger. What could potentially be the problem with having a magnesium engine block? Overheats, and then what happens? It catches on fire, can you put it out? It never goes out. Right? And sometimes the firefighters would come and they go, oh, we can't even put water on that engine, because the engine was so hot and it's burning at such a high temperature that you spray it with water, sometimes cause an explosion because the water would turn to liquid gas so rapidly that it would explode in steam and people around you could be burned, so you basically had to let the Volkswagen burn out. So that's why they don't make engine blocks out of magnesium anymore. When I was in high school back in the 70s, the late 70s, we knew this, that the Volkswagen engines were made of magnesium. Some of the fellas in high school would go and get a whole junk Volkswagen at a junkyard, take the engine out, take all the pieces out, just have the block, the engine block, and they bring it out to these desert parties, this place that we used to call the dunes. The dunes, and we make a big campfire, and they put the big engine block on top, and they light the campfire, and it makes such a gigantic hot flame that you couldn't keep a normal campfire if you stand like this and warm your hands. The engine block fire, you had to stand way back, and it was so bright that you could see where the party was, way far away, and to do that, you know how to drive and get out to the party, the desert party. So once again, don't try this at home. These are not good ideas. I'm just telling you this as anecdotal stories to help you remember this stuff. Okay, so those are combination reactions when you take two small things and you make one larger one. All right, you know I shouldn't have changed that. All right, the next type we're going to talk about is decomposition reactions. And decomposition reactions are basically kind of the opposite of the combination reactions. Combination, you take two small things, you make one big thing out of it. Decomposition, you're taking one big thing, breaking it up into other smaller components. There's a good YouTube channel video about a particular decomposition reaction. I'm going to show you one on the overhead here. That is one that I used to like to use when I was talking about decomposition reactions when I used to do demonstrations. Does anybody know what the formula for this stuff is? Hydrogen peroxide. Did I tell you my chemistry cat joke about hydrogen peroxide? No, okay, on the internet there's a character like Grover Cat, except he's Chemistry Cat. And Chemistry Cat always has good chemistry jokes. Here's a Chemistry Cat joke. Two cats walk into a bar. Bartender says to the first cat, what do you want to drink? The first cat says, I'll have a glass of H2O. Bartender says to the second cat, what do you want to drink? The second cat says, I'll have H2O too. The second cat died. Right? Silly chemistry tattoo. All right, the decomposition of hydrogen peroxide, we have a liquid solution. It decomposes. If you've ever, like when I was a kid, my mom used to use hydrogen peroxide to clean holes. We did a lot of skateboarding and roller skating when I was a kid. And you fall down on skateboards or roller skating, everybody used to do is scratch up your knees, and you know, the asphalt and dirt and the chunk in your knees, right? So we come home crying, and Mom say, sit down. She take the hydrogen peroxide, she pour it on her knee. What happens? What happens when you pour hydrogen peroxide? It bubbles a whole bunch. That's the decomposition. Now, the hydrogen peroxide is good for a wound like that, not because it disinfects the wound. It's not an antiseptic. It doesn't kill germs. What it does is if you have particulates and dirt and junk in a wound, anything that is an organic substance will catalyze the decomposition of hydrogen peroxide, meaning it makes it happen faster. So you can take a hunk of meat, which is basically the same as what your wound by your knee was. You can take a carrot, an apple, anything organic, put it in some plain old hydrogen peroxide from the drugstore, and you'll see a whole bunch of bubbles coming up. So the decomposition is catalyzed by organic material, and that's what it did. It bubbled all the junk out of your knee. Those bubbles, what do you suppose those bubbles were made of that were coming out of the hydrogen peroxide? H2. Oxygen gas. Now, it would not be good to have the H2 gas coming out, right? Because if you were smoking while you were pouring the hydrogen peroxide, you might have a series of little small explosions with the hydrogen gas there. Well, if oxygen gas is what's coming out of there, what else is left over after we take some oxygen out of H2O2? Good old H2O, right? So, the decomposition of hydrogen peroxide, you take the big molecule, make up small things. Is that balanced? Don't think so, because we've got two hydrogens there, two hydrogens there. I got two oxygens, I got two there, but then I only have one more there. I have to count all three oxygens on the product side as part of my balancing of the equation. So how could I fix that to make sure that it's balanced? We can start with two of these, right? That might work, right? And I have two H2s, so now I have four hydrogens. How do I fix the hydrogens over here? Put a 2 in front, right? Now I got four hydrogens on each side. How many oxygens do I have on the reacting side here? 2 times 2 is 4. Here I've got 2, right? How many more do I have here? 2 more. So now that equation is balanced. It follows the law of conservation of matter. Okay? Now, hydrogen peroxide is not only catalyzed, the decomposition of hydrogen peroxide is catalyzed not only by organic material, but it's also photocatalyzed. What do I mean by photocatalysis, or that it is photocatalyzed? Light makes it break down and decompose. So why do you suppose they sell the 3% hydrogen peroxide at the drugstores in those brown bottles? Because it doesn't let what through it? Light. If they sold it in clear bottles where the light could hit it, what would you be buying a bottle of? Water. We don't want a bottle of water, right? We want a bottle of hydrogen peroxide. That's the 3%. The kind that you buy at the drugstore is the 3% hydrogen peroxide. It's pretty dilute. In our stock room, we have 30%, which is basically 10 times the concentration of the 3%. Now, the stock room bottle also is brown, which is kind of interesting. The stock room bottle looks sort of like an accordion, a part of the bottle, right? The stock room bottle with the H2O2. And what happens over time is this how it's at the start. This is what it looks like. Over time, the bottle changes. Right? Why does the bottle expand? It's decomposing, and we're getting oxygen in there. So what the biotech has to do is she goes in there, she unscrews the top, she smooshes it down, right, to this side, screws the top back in, and sets it back on the shelf. 6 months later, it looks like this again, right? She unscrews the top, smooshes it down, screws the top back on. So we have to be careful and monitor the growth of the bottle of the 30% because it is 10 times the concentration of the 3%. This stuff can also be pretty toxic too. 30% hydrogen peroxide. All right, so that's an example of decomposition. Sure. There's where the convention can change. You're absolutely right. You use the IUPAC rules, which we generally use, which would be dihydrogen dioxide. In this case, that's more like the common name or the slag name using a different system is hydrogen peroxide. So add hydrogen here. Like water is water versus dihydrogen monoxide. So it's kind of just the slang version of it. Yeah, yeah. Well, and it has to do with the oxidation state of oxygen, which is weird in hydrogen peroxide. Okay, before we can get on to single and double replacement types of reactions, what we really have to discuss is this concept of an aqueous solution. It's a very, very specific type of solution to a chemist. And an aqueous solution has to do with taking a salt. Now, the salt could be a binary ionic salt. It could be a ternary ionic salt, but how do we know something is a salt by just looking at its chemical formula? Has a metal and something that's non-metal in the same compound, right? So if we look at something and it has a metal and a non-metal, we say it's a salt. The next thing we ask ourselves is this salt soluble? Now, in everyday American vernacular, soluble means that you just put it in water and it appears to make, it dissolves and it makes a homogeneous solution. As chemists, this idea of solubility is much more specific. When I say something is soluble, what that actually means is when I put an ionic salt into water, whether it's a binary ionic salt or a ternary ionic salt, those ions, once they hit the water molecule breaks them up into their component ions. So let's watch an animation of that, and then we'll talk about the specifics. Okay, that is not the animation I want. Let's see here. All right, here we go.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
They appear to disappear. All right? That's what happens. Now, I'm going to give you a drawing explanation that is a little bit more specific than what you saw in the video. Okay. Aqueous solution. What that means when you create an aqueous solution is you take a salt and water. And the salt needs to be soluble. And we'll talk about soluble when we get to the double replacement reaction ideas. But basically what soluble means is when I have something like NaCl, and I represent NaCl with this formula unit idea, meaning it's the lowest common number ratio of things in a compound. If I actually looked at a piece of sodium chloride, like in the video, I would have sodium and chlorine and sodium and chlorine and sodium and chlorine all hooked together in a three-dimensional structure, right? So repeating crystal structure. I take that sodium chloride hunk of salt and I plop it into water. Okay? I drop it down into water. What happens is water molecule, if we look at the individual water molecule itself, here's what water molecule looks like. It looks kind of like Mickey Mouse. The hydrogen side, the H2 and the O, the hydrogen side of the water molecule is positive because those hydrogens are each positive, both of them orbiting on one side of the molecule makes that half of the molecule positive. If you remember from molecular geometry in Chem 130, the water molecule also has two non-bonded pairs of electrons on the other side, which make this side of the molecule negative. And we call this molecule polar, meaning it has a positive side and a negative side. Keep in mind the positive side is where the hydrogens are. So hydrogen ions approach each of these things. And when sodium and chlorine make a crystal, remember that it's an electron transfer situation. The sodium gives up an electron. Metals only have 1 or 2 or 3 valence electrons. The non-metal takes that electron, and that creates a situation where the sodium is positively charged because it's lost some of its negative charges. The chlorine is negatively charged because it's gained them. So what keeps these two things together are these bonds, the force of the electrostatic difference between them. Pluses and minuses attract, right? Opposites attract. So this bond takes energy to break, and we call that energy the bond energy. We'll be talking a lot about that idea of bond energy later on in the course. The amount of energy it takes to break that bond varies depending on the charge of the ions, as well as the attraction that each of the ions feels for each other, as well as the size of the ions. So that bond energy changes depending on how much energy it takes to break that individual bond. So if a water molecule orients itself and starts to approach chlorine, here's a water molecule just floating around the water. Once it starts to approach chlorine, it will turn itself so that the positive side of the water molecule is oriented towards the negative ion of chloride in that structure. Now, these two things, the sodium and the chlorine, have an attraction for each other. That's what keeps it together. So it's a pretty strong attraction, that bond energy. One water molecule is not going to be able to take chlorine and break those bonds. A single water molecule doesn't have the required energy or attraction to pull it off. But if multiple water molecules kind of gang up on that one chloride ion and they all start to approach it, then all of a sudden that bond can break, that bond can break, and that bond can break, and chlorine ion or chloride ion will break off of the structure of the crystal and start floating around on its own in the solution. Once it breaks off, that breaking off process is called dissolution. It's breaking it up. Once it has dissolved and it's gone through this dissolution process and the water molecules surround the chloride ion, they surround it in such a way that the positive part of the water molecule is oriented towards the negative ion. See how I'm putting the little Mickey Mouse ears all towards the chloride ion? And that creates a buffer. This step is called hydration. So there's a dissolution step. That requires some energy. This requires another energy step, this hydration, the water molecules surrounding the chloride ion. Same holds true of the sodium. So sodium ion breaks off. Now it's positively charged. It will be hydrated by the water molecules in a similar fashion that the chlorines are hydrated. But now the water molecules turn it so their little ears, the Mickey Mouse ears, are on the outside. So look at how the water molecules orient themselves around sodium versus how they orient themselves around chlorine. Each of those orientations is hydration and provides a buffer. So do you suppose that when these are in solution, do you suppose this negatively charged chlorine is attracted to the positively charged ion sodium when it's in the solution? Are these two attracted to each other? Is a positive and a negative attracted to each other? Yeah. Absolutely they are. Well, what happens is this shell of hydration, even though they are attracted to each other, the shell of hydration, when they come into contact with each other, it will make them kind of bump off each other. And it will keep them from recombining and forming the crystal anew. So it takes energy to break them apart. It takes energy to hydrate them and make the water molecules shell around them, and that keeps them from coming back together. Now, if I wanted to get the salt crystal back out of the water, what could I do to get the salt out of the water? I just dry out the water. Right? In Arizona, you can put out the sun for a couple of days. If you're in the lab, you can put it on a hot plate and boil it. And what would be left at the end of the boiling or the evaporation phase? The salt in the bottom would be the same size, shaped crystals. They would all be cubic. And what happens there is this. So when they're completely hydrated and they come next to each other, they bounce off each other because they're completely hydrated. Once you start taking out some of those water molecules, evaporating some of them, the shell of hydration no longer exists. And when they are coming in contact with each other, then all of a sudden, instead of bouncing off, they connect. And that bond energy then is contained when they connect. So it takes energy to break them. Energy is put back into the system when the two things come together and make the crystal. Right? So that's this idea of dissolution of a soluble substance. That's a binary ionic salt, right? Like NaCl. When I put it in water, we can have a ternary ionic salt. we can put that in water. And it's important that we recognize the types of elements that are going to be the ions in solution. If I put lead nitrate in water, what kind of ions would I have in this particular aqueous solution? I have some lead ions. What would be the charge on my lead ions? +2. What else would I have in there? This goes back to your Monty nomenclature. I have some nitrate polyatomic ions. So what would be the ratio of nitrate to lead? 2:1. All right. So we know we can't just put a single piece of lead nitrate, right? Because ionic substances are the big crystal structures. I can't just take one little formula unit and put it in water. But what I'm representing here, sort of microscopically and somewhat symbolically, is the fact that I've got a 1:2 ratio of lead to nitrate ions in solution. It turns out later in this course that ratio idea is going to be very important. When we get to Chem 152, it's going to be uber important that you recognize that those ratios are true because you expand that to the idea of concentration. If I have a concentration of PbNO3, say of 10, I'm going to have a concentration of 10 for the lead and a concentration of 20 for the nitrate. See what I mean? And the concentration of the ions doubles. These ions are what we call, anytime you put ions in solution, whether it's a binary salt like sodium chloride, you get those kind of ions in your solution, or whether it's a ternary ionic salt like lead nitrate, you get those kind of ions in solution. All these ions are called electrolytes when they are in solution. Why are they called electrolytes? What does an electrolyte do when you put it in solution? Conducts electricity, right? That's what an electrolyte does. And it conducts electricity because some of these things are negative and some of these are positive. If you had purely distilled water, only H2O, it would not conduct electricity. We did not put a light bulb with a conductivity apparatus in it and have a light bulb light in purely distilled water. You have to have ions in solution in order for it to be an electrolyte, in order for it to conduct electricity. That's why when you drink Gatorade, they say you're adding electrolytes to your body, right? If you look at the label on Gatorade, there's a whole bunch of ionic salts, binary and ternary ionic salts. When you put them in water, they're all soluble. You drink the Gatorade, you have ions in solution. It helps your body with conducting electricity. Our cells need to conduct electricity to communicate with each other. Our synapses in our brain need to conduct electricity to communicate memories. If you get dehydrated, you'll notice your brain doesn't work as well. Your organs start to shut down because they're not communicating to each other. So when you get dehydrated, drink Gatorade because it has electrolytes and allows your body to conduct electricity in solution. All right, so those are the salts dissolving in water. Now, and once again, I would encourage you to look at all the animations that I've put in here. I don't have time to go through them in class. Now we can talk about single replacement reactions, also sometimes known as single displacement reactions, also known as redox. Yes?
So regular tap water has
Regular tap water has all kinds of electrolytes in it, and that's good. We actually, physically, it's probably a bad idea, if you check this with a biologist, but it's probably a bad idea for us to drink distilled water. Yeah, because it doesn't have any ions in solution. Personally, I drink tap water. I have a little RO system in my sink, and it does put through and gets all the chlorine and some of the other ions out, but I think it's important to drink some water with some ions in it. Now, smart water, what they do is, they take regular water, they distill it, and then they add salts to it, so they can have electrolytes, which I think is kind of fun. The distillers take all the ions out, and then they add synthetic salts in there, and it tastes like better, smart water. So smart water is supposed to make you smart, right? It has electrolytes and it helps your brain conduct electricity. Did that answer your question? Okay. So single replacement reactions, the general form of a single replacement reaction, let's get back to our overhead here. General form of single replacement reactions is going to look like this. Single replacement reactions. The general form is you're going to have some solid metal. Whenever you see a metal with an S next to it, it looks like just like you would find on the ground. You know, a hunk of copper, a hunk of iron, a hunk of aluminum. You're going to put it into some aqueous solution, so some ionic salt in aqueous solution. That's what it means. Aqueous solution means you've got an ionic salt, you put it into aqueous solution, and now you have the ions floating around. So that would be the symbolic representation. What you think about, you say, oh, okay, I have an ionic solution of this BC. What that means is I'm going to have B ions and C ions floating around. How come I made the B ions be plus and the C ions be minus? Metals are always positively charged. We always depict the metals first in an ionic compound or a salt. All right, so I got B ions and C ions now floating around in my aqueous solution, right? Because that's what we're thinking of when we think of aqueous solutions. And in I plop my hunk of metal A. All right, so there's metal A. Right? There will be a reaction, calculus people, if and only if, right? If and only if A is, as a solid, more active than B, then a reaction will occur. Alright, how do you know if A is more active than B? How do we know that? There's a reference that we need to use for this. What's the reference? The activity series. Called the activity series for metals. And I've given you a handout with a periodic table on one side, right? There's a periodic table on one side. You turn it over, you've got solubility rules, and these are used for double replacement reactions. We'll talk about those in lab more. Here is the activity series for metals. Take a look at this. Here are the most active. These are the ones that are the least active. So there's the ranking of all the elements that you might come into contact with, the most active to the least active. So the A would have to appear up here before the B in order for the reaction to occur. So the metal that's the solid has to be more active than the aqueous solution. So what happens there is now B comes out of the solution. B comes out of the solution, and what else are we going to have besides B when it comes out of the solution? We're going to have AC now in aqueous solution. We've got some animations that I really like that were made from the University of Iowa. Let's see if we can get in there. Here we go. Look at these animations, which I think are super spiffy. All right. Let's start this animation. I know not to click that. All right. Here they give us some choices of aqueous solutions. I'm going to start activity 1, so it's going to limit my choices of aqueous solutions to 4. Here's my 4 aqueous solutions. I've got magnesium nitrate. So what kind of ions are floating around in this solution? Magnesium and nitrate in a ratio of 1 to 2, right? What about this solution? Zinc and nitrate. This one must have copper and nitrate. Why do you suppose that one's blue? Well, look at it from a science perspective. They all have nitrate in them, right? So it must not be the nitrate that's making it blue. What must be making it blue? Copper. When copper ions are in solution, the solution appears blue. Yep. You will notice if you've ever had tropical fish aquarium, sometimes the tropical fish get this disease called ick. And you'll know that the fish have ick on them when they start, they'll swim and they'll kind of like, it's an itchy parasite. And they'll swim up next to something, they'll try to rub their side, or they'll rub next to the bottom of the aquarium trying to rub it off because it itches them. And what you do is you get this ick medicine from the pet store, and you measure out, depending on how many gallons of water you have in your fish aquarium, and you pour this ick medicine in and it's blue. I'm like, that's interesting. I look on the back of the fish ick medicine, and right there is copper sulfate. So copper sulfate must be one of the active ingredients to cure this ick. And I know that copper compounds are actually fairly helpful in medicine, and a lot of Eastern and Chinese medicine use a lot of copper compounds and copper salts because it does have some interesting characteristics. And then finally we have the silver nitrate solution over here. I'm going to pick zinc as my metal that I'm going to put in each of those 4 aqueous solutions because I know that zinc is a fairly active metal. It's fairly high in the activity series. So it's going to react with some of these and not with other ones. Now I want you to notice the color of the solution, and the color of the zinc is gray to begin with, and that's what zinc kind of looks like. The color of the solution. And now when I put the metals down into the solution, watch what happens to both the solution and the metals. All right. I'm not going to move the metals yet because I want you to notice the solution. Do you think there was anything on a chemical reaction here? Doesn't look like it. Do you think there was a chemical reaction here? No. Well, that makes sense because if I put zinc metal into a solution of zinc ions, one's not more active than another, so that makes sense that it's not going to react. Okay. How about this one? What could we conclude about zinc and magnesium since there was no reaction? Magnesium must be the one that's higher on the activity series, and you can double check that on your tables that I gave you, right? Isn't magnesium higher on the activity series? All right, so that's why there was no reaction. Well, now we look at the copper and the zinc. Why did copper and zinc react? Copper's actually, zinc is actually higher on the activity series. It's more active. All right, so there's a coating on the outside of the zinc that's kind of coppery colored. What do you suppose that coating is? Copper, most likely. Okay. And what do you notice about the color of the solution? It got less blue. So if blue is the indicator that you have copper ions in solution, if it's less blue, what must have come out? Some copper ions. What must be the coating that's on the outside of that zinc? Copper. All right, that makes sense, right? That's why I like this animation, because it's good visuals, good macroscopic perspective, and I don't actually have to use the chemicals in front of you guys, right? All right, this one here, the silver nitrate, what's the difference in the solution here versus the solutions here and here? It's kind of cloudy. A little cloudy. So that's your first indicator that for sure a chemical reaction has taken place. And what do you notice has happened to the zinc in the silver nitrate solution? It looks like it got coated. Doesn't it look like the zinc is kind of coated with something like it's coated on the copper? It's also coated in the silver solution. Well, if it's copper that coated the zinc on the copper nitrate solution, what do you suppose the coating is in the silver nitrate solution? Silver. All right. So now what we're going to do is we're going to look at the microscopic, which is my favorite part of this animation. I'm going to take zinc and I'm going to drag it down here to the copper nitrate and put it in there. All right. And now what they're going to show me is it's going to zoom in on the microscopic perspective and it's going to show you the atoms and molecules involved. But before we do that, let's think about what's in that beaker that is going to be reacted potentially together. So we look and say what has to be in that beaker. So I'm going to start out with zinc metal, right? Zn solid. Plus my solution, I believe, was copper nitrate, right? Was it CuMnO3 too? Just CuMnO3. CuMnO3 too. Alright, so there's my aqueous solution. So now in my mind's eye, I want to think about what was going on in a microscopic perspective. So here's my beaker, right? Here's my solution of copper nitrate. What kind of ions are in my solution of copper nitrate? Copper ions that have what kind of charge associated with them? +2. And what else did I have in my solution? Nitrate, polyatomic ions. And what's the ratio of nitrate to copper? 2 to 1. Okay, 2 to 1. Right? So in comes my zinc. And in the picture, right, shows a bar of zinc. And it's being put down in solution. And all of a sudden you get this fuzzy stuff on the outside of the zinc. And we said that that fuzzy stuff, this stuff here, this is the coating, what's that, the identity of that? The copper solid, right? Plus, what else am I going to still have remaining in my solution? Zinc and nitrate. Now, I have to write new nomenclature for my products. The good thing about these reactions, it's different than single replacement reactions, is, oh no, this is single replacement reactions. The bad thing about these is the charges change. Anytime you have a metal solid, it has a 0 charge. Here we know that copper was +2. When copper comes out of the solution, it's going to have a 0 charge now. And zinc, what's the charge on zinc as an ion? You guys know that? +2. All right? And this is going to be my aqueous solution. All right, let's look at the animation of what that looks like on the microscopic perspective here.
Can you explain that charge again?
Sure, just a sec. Let me get to the animation. I think the animation will do a better job than I can at explaining the charges. Here we go. All right, so now there's my experiment. I'm going to start it, and we're going to look at the microscopic perspective. Copper ions are floating up. Boom! Look at that. Oh, that's so cool. I love this animation. Let's do it again. All right, what they're saying now is the nitrate and the water ions have been taken out. So really in the animation, here's what you should think about. They're saying, okay, just because we know that nitrate's not doing anything, we're just going to take those out of the animation. They're still there, right? And we're just taking them out so they don't get in the way and confuse you. So really all they're showing is the copper ions floating up to the hunk of zinc. Let's watch that again. All right, close that. Now, as the copper ions float up, look at their size. Boom! What happened when copper ions touched a piece of zinc? They took electrons from who? Who gave them the electrons? The zinc. The zinc gave them the electrons. The copper received the electrons. That's why we call it redox, oxidation reduction. Redox, by definition, is a transfer of electrons between metals, in this case. All right? Look at the size. Let's try that one more time. I want you to watch the size of the ions both before and after they exchange electrons. Copper's small. Zinc is big. Electrons are exchanged. What happened to the size of the copper? Well, it got bigger. It got bigger than it was originally. And that makes sense, right? If it's small, because it's missing some valence electrons, and all of a sudden it gets some valence electrons, it makes sense it would get bigger. And if you're a zinc atom, which has all your valence electrons, and some copper comes up next to you and steals yours, does it make sense that you're going to get smaller? Okay. And they swap places in solution. That's what you also need to recognize, is watch that. First, the copper ions are in solution. They're floating around. And the zinc is solid. They exchange. And the zinc ions go into solution. Now the copper has coated the zinc. This process is called electroplating. You drive a vehicle, when you drive an automobile, that has two large hunks of electroplated metals in the front and back of your car. One of those two large hunks of electroplated metals. Your bumpers, they are still the bumpers, right? Bumpers are electroplated. The inside of the bumper, who knows what's the inside of the bumper made out of? Iron, steel, basically, is iron. It's cheap, it's heavy, it's very resilient, it resists crunching. What's on the outside of the iron bumper? Chromium atoms, which are pretty and shiny, but they're expensive, right? You would want to make a whole bumper out of chromium ions. So what you do is you make a big bumper out of iron, you take that big honking bumper, you lower it down into a vat of chromium ions, and that happens. The chromium ions grab onto the iron gives up some electrons, chromium takes them, makes a nice shiny coating on top of your iron bumper, and that iron bumper now won't rust when it comes into contact with the air because chromium is much lower on the activity series than iron is. And in this case, to make a chromium bumper, you actually have to put electrical current through the iron bumper in order to get it to react. You know about that kind of stuff, that's electrochemistry, when you get to Chem 152. Question?
I do have a question. Just something I thought was, so when you put in, like, for example, zinc inside of it, the zinc is almost more willing to, like, the activity that it has is more giving. It's not as hard, it's actually more, because I always thought the opposite. I thought
That's taken, right.
It's more strong.
Yeah, it has to do with the given part.
It's actually a lot more giving.
It has to do with the given part. So the zinc is more ready to give up its electrons than things that are lesser than it is. And so that's why you put a zinc down in there. You can force that reaction to happen, like I said, by adding electrical current through it, and it will force ions to plate on it. If the activity of one metal is less than another, you can force it to plate. So this is actually very helpful in everyday life. There's all kinds of plating. If you have jewelry, like gold electroplate jewelry, they take sterling silver, and it's much cheaper to make a ring or a piece of jewelry out of sterling silver than they put it in a vat of gold ions, and they electroplate it, and it looks like gold. Ooh, pretty, until you polish it too hard, right? You polish it too hard, you rub off that thin layer of gold atoms, and you look and you go, wow, that was cheap. That's sterling silver that's plated with gold rather than a gold ring, right? Okay, so check out those animations. Those are kind of fun. All right, that's single replacement reactions. Now, evidence, visual evidence that you will see, macroscopic evidence. When you do this kind of reaction, you'll see one or two things as evidence of a chemical reaction that is single replacement reaction. Either a precipitate forms, just like we talked about, right? Sometimes the precipitate will cling to the piece of metal. Sometimes if it makes a lot of it, the precipitate will start to fall off that metal. go into the bottom of the container, you'll see that. The second visual evidence that a single replacement reaction has occurred is bubbles forming. What is your indication? What does that mean is happening? If you see bubbles. What's formed when you see bubbles? A gas. Okay. So you either see bubbles or precipitate, and that gives you the idea that it's a single replacement reaction. Okay? All right, there's demonstrations, the macroscopic perspective. There's some really cool ones. Some of these can be really exothermic. If you did, okay. All the chemistry teachers wrote a lab, well, we wrote quite a few labs, so the common theory lab, most of you guys can talk to the publishers. Do you remember the lab where you took the copper ore and you refined it, you crunched that, and you put it in acid, and you put aluminum in, and get the copper out of it? Remember when you put the aluminum into the copper sulfate solution? It's very exothermic, it got really hot, bubbled, it was a really cool, vigorous reaction. Well, that's actually a reaction that they use in copper mines, like in Evoy, load. To actually take that reaction. I wrote that problem. After I saw a similar reaction done at South Mountain Community College, I went, ooh, that's a super cool Arizona lab where you take an ore like malachite or azurite or turquoise is even an ore of copper. You dissolve the ore in acid, which liberates the copper ions, puts them into solution as copper +2. Then you take a hunk of aluminum, which is more active than copper, and this is what they do in the mines. They put the aluminum down into the copper, vigorous reaction occurs, the copper precipitates out of the solution, the aluminum goes in, aluminum is a lot cheaper, right? Copper we want out, aluminum goes in, then you take the precipitate and it's pure copper. So that's how the copper mines actually mine copper, and there's some good demonstrations there of similar things. All right. A gold mining, I think they do, because gold is very low on the activity series. So gold would be, gosh, they used to make pipes out of copper. Pipes in your home, old homes will have copper pipes in them. Copper is good because it's very low in the activity series. Gold is even lower though. Why didn't we make our pipes out of gold instead of copper? It'd be a little expensive, right? So you have copper pipes, pour stuff down in, bleach or swim pool acid or lots of things that are caustic and might react. Since copper is low in the activity series, it doesn't react. Well, now we don't use copper so much for pipes anymore. What do we use now? PVC pipe, which is polyvinyl chloride, which is an organic compound. And anytime you have an organic compound, I'm not an organic chemist, you have to worry about the hydrocarbon base of organic chemistry. If you purchase a new home, I would probably run the water through all of the faucets and everything that you drink out of for probably a period of 24 to 48 hours to get all of the residual polyvinyl chloride adhesive and stuff out of the pipes before you actually start drinking that water. So if you're brand new home, be careful with PVC pipes because those sometimes can be soluble in water. All right, double replacement reactions. Double replacements are similar to single replacement, and then we got aqueous solutions. But double replacement reactions are aqueous solutions that are added together. So if we look at what that looks like on paper, I'm talking about double replacement now. All right, the general form for double replacement reactions is going to be two aqueous solutions, right? That reacts. You say, all right, here's one aqueous solution, we call it AB, and A ions and B ions. The second aqueous solution, we have C ions and D ions. I pour them all together into one giant container. What are the potential products that might have hooked up to make a precipitate in this case? In this double replacement reactions, you're going to see the same evidence. Macroscopically, you're going to see either precipitate form or bubbles. So single replacement and double replacement reactions, the visual evidence of the chemical reaction is the same. Macroscopically, you're going to look for a precipitate or bubbles forming. What could be the potential products here of these two things? A and D, good, I like that because you always put the positively charged ion first and the negatively charged ion second. What could be the second potential product? C and B are put together. You always put C first because that's the positive ion and B second. So there's the general form. Let's talk about something a little more specific rather than just the general form of the equation. Look at something a little more specific and say, all right, for example, here's my favorite double replacement reaction because it's a really pretty reaction. One of them is a binary salt, the other one is a ternary salt, right? At this point, you should know those vocabulary terms and should be able to pick that out. I might ask you on the exam next a week and a half, give you a list of salts, which one of these is binary, which one of these is ternary, right? You should be able to pick that out. All right, I put these in together. Actually, let's talk about what's in them individually. So I have two containers of aqueous solutions. In this container of my aqueous potassium iodide, what kind of ions will I have in the solution? Potassium ions with a +1 charge, and what else? Iodide ions with a -1 charge. In my other solution of lead nitrate, what kind of ions am I going to have? Lead ions, with what kind of charge on the lead ions? +2, and what else? Nitrate polyatomic ions in a ratio of 2 to 1. Right? I put these together in one big container. What are the potential products that might come out of this double replacement reaction? Potassium and nitrate might hook up, right? What else might hook up? Lead and iodide. All right, the crucial part here is you need to make sure you write new nomenclature for products. Unlike single replacement reactions in which the charges on ions change, which makes it a little confusing, the charges on the ions in double replacement reactions do not change. Whatever the charges are as reactants are the same charges as they are products, which makes your job at writing new nomenclature a smidge easier. But you gotta be careful. Over here you say, all right, I know potassium is +1. I know that nitrate is -1. I know that lead is +2. I know that iodine is -1. Right? All right. Is this nomenclature correct for lead nitrate, or excuse me, for potassium nitrate? It is. We're good there. How about this nomenclature? Not so much. What are we going to do to fix that one? I need a 2 subscript for the iodine, right? All right. Now I need to balance this equation. Is it balanced as is? No. What are we going to do to balance it? 2 here. All right. That fixes the iodide, but now it messes up the K, potassium. So maybe a 2 there. That balances the potassium, and it also balances the nitrate. So now my equation follows the law of conservation of iron, right? Now it works. Okay, so that's double replacement. One of the products is going to be an insoluble salt. Okay. You don't know at this point how to determine which one is the insoluble salt. You won't have to for the first unit exam, but you will have to for the second unit exam. This one is going to be your aqueous solution. We'll talk a lot more about how to determine who is which thing. Which one is the insoluble salt, in which case you would put solid, or the soluble salt, in which case you would put AQ, and learn how to designate which one is which in lab. All right, so let's go back to our PowerPoint. Those are double replacement reactions. Once again, you're going to look for visual evidence of either a precipitate forming or a gas forming. And finally, combustion reactions. Combustion reactions happen quickly, and generally you're going to take some sort of a hydrocarbon, burn it in air with oxygen to create carbon dioxide gas and water with complete combustion. If it's incomplete combustion, meaning you don't have enough oxygen, instead of CO2 in a lot of your products, you're going to get carbon monoxide. Like cars, exactly. Right? Cars are excellent emitters of carbon monoxide. But if we breathe carbon monoxide, it's not poisonous in and of itself. What happens is carbon monoxide hooks onto our hemoglobin and doesn't allow it to carry oxygen through our blood, and eventually we suffocate because carbon monoxide is more adept at taking that little spot on your blood cells than the oxygen is. So you don't want to use that and have combustion. We are also combustion reaction engines, right? We inhale oxygen, right? That's a reactant. The food that we ate is burned, and we inhale the oxygen. We exhale carbon dioxide, right? And that's when we produce carbon dioxide and water vapor. So we can prove to you that we make water vapor. It is. It's water vapor. So we exhale. We are internal combustion engines. Carbon monoxide is, of course, produced from automobile engines, which is really bad for us to breathe. So we don't want to breathe any carbon monoxide. All right, formula weights. How do we calculate a formula weight? Formula weight, the term formula weight is the same as molar mass. So basically formula weight We'll do a calculation of that. All right, formula weights. Formula weight is basically the same thing as molar mass. Formula weight is generally refers to ionic substances, right? Salts. Molar mass generally refers to molecular or covalent substances. And what formula weight or molar mass is, it's the same definition. It's the mass of 1 mole of any compound. That compound can be ionic, called the formula weight. That compound can be molecular molar mass. All right, this idea of 1 mole. Now, mole in chemistry is different than a mole in biology, right? Mole in biology is a little furry animal with kind of squinty eyes that just tells under the ground, right? That's one kind of mole in biology. Another kind of mole in biology, there's another kind of mole in biology, a precancerous skin lesion. Right, this is a mole in biology. And mole in chemistry, what's a mole in chemistry? Okay, there's a number associated with it. Here's Avogadro's number. And a mole of something is that many pieces of that stuff. 6.02 times 10 to the 23rd pieces. So if you looked at that in terms of a real number, I would take this decimal and move it how many places to the right to get a real number out of that? 23 places, so it's 602 and 21 zeros. That is such a huge, gigantic number. It kind of boggles the mind to even think about. Bakers deal with a much more reasonable number, a dozen, right? 12, we can count 12 pieces. People that provide office supplies deal with a much more reasonable number. They talk about the gross. The gross is a dozen dozens. How many pieces is in a dozen dozens? 144. Okay, we can count to 12. We can count to 144. Can I count out a mole of pieces? If I started from the moment I was born and started counting, and I never took a nap, and I never slept, and I never stopped counting, and I got to the age of 90, from the time I was born to the time I was 90, I would not be able to get to a mole. That's how many moles. If I had a mole of pennies, 6.02 times 10 to the 23rd pennies would be a very sufficient paycheck for my entire career. I would happily accept a mole of pennies in any shape, any form, for my paycheck for an entire career. Because if I got a mole of pennies right now, I could spend $1 million a day for the rest of my life without until I was 90, right? Then I'd have enough inheritance. I got 2 sons. I could divide up the inheritance after I die when I'm 90 amongst my 2 sons. Each of them, when I died at 90, could spend $1 million a day for the rest of their lives, and there'd still be money left over for my grandchildren. So mole's a lot. I had a mole of baby marshmallows. Remember kind of ones that we put in hot chocolate? Okay? And I took those baby marshmallows and put them on the entire surface of the planet, all the continents and all the oceans. We would be 6 feet deep in baby marshmallows. So it's a gigantic number. We can't ever count it out. So why do we use this quantity? And we can use this with relation to formula weight or molar mass. If I want to count out a mole of carbon, I can't do that. But if I look at the periodic table and I see that the molar mass of carbon is 12.01, and I put units on that like 12.01 grams per mole, could I go out into the balance room and take a container of carbon atoms and weigh out 12.01 grams of carbon atoms? I could do that fairly simply. It would take 90 years, would it? It would take me a couple of minutes. Okay. That's the formula mass. So it takes us from what we can't count and we can't see, right? We can't count out a mole. We can't count out a mole of atoms to what we can count and we can measure, in this case, mass of a substance. So if you look at something like, here's lead nitrate here, just because it's a nice easy compound. I want to know the formula weight. The question on your exam will be, what's the formula weight for lead nitrate? You go, formula weight, molar mass, same thing. I know my units are grams per mole. So I got to add up the individual components of that thing. I have 1 lead. And I look at the periodic table, I look at lead, and lead is 207.2 grams per 1 mole of that stuff. Times 1 mole gives me 207.2 grams. For that part of my compound. Now, if I look at lead nitrate, how many nitrogens do I have in a unit of lead nitrate? No, 1, 2. That subscript on the outside counts for everything on the inside. So I actually have 2 nitrogens. Each nitrogen is 14.0 grams per mole each, times 2 pieces gives me 28 grams if I had a mole of nitrogen. If I look at this compound, lead nitrate, how many oxygens do I have in that compound? 6. 3 times 2 is 6. So I got 6 oxygens. I generally tend to round these to the nearest tenth, right? Oxygen is about 16.0 grams per mil. Let's see. 32, 64, 95, 96. Add all this up. So 331.2. Did my math right? So, if I said I need to make a solution that has 1 mole of lead nitrate in it, how much would I go weigh out? 331.2 grams of the stuff, and I'd go, how many pieces of this stuff do I have in there if I have 331.2 grams? How many pieces are there? A lot. How can we quantify the number of pieces in there? We have 1 mole, or 6.02 times 10 to the 23rd pieces of lead nitrate. I find that pretty remarkable. That you can go from something you can't see, you can't count, to something that you can see, you can't measure. Right? So that's pretty helpful for us in chemistry. We can also use this information to figure out the percent composition. For example, if I want to know what is the percent nitrogen in lead nitrate, that would be the question that you would be asked. Alright, so percent, what's the formula for percent? Chemists love percent for so many things, so you just gotta make sure you know this formula. What's the formula for percent? Part over total or whole, and this is the percent, what do we do with the rest? Times 100. Alright, so percent nitrogen, what's the part that was nitrogen? 28 grams, right? So we put 28.0 grams, what am I going to divide it by? The total, 331.2 grams times 100, and that gives me the percent nitrogen in the compound. All right, pretty easy peasy so far. We're still leading up to the big picture stoichiometry, so we're getting some smaller skills that we have to accrue and scaffold before we get to the big skill, which is stoichiometry. All right, so formula weight, molecular weight, basically the same thing as formula rate. How much does a mole of it weigh? All right. Avogadro's number, 6.02. We've already talked about that. If you say a mole, it's a mole of bunny rabbits. You could have a mole of bunny rabbits. Molar mass, grams per mole. That'd be a lot of bunnies. That'd be more bunnies than we could handle on the face of the earth, right? If baby marshmallows covers us 6 feet deep, bunny rabbits would be a heck of a lot of bunny rabbits. Keep it in mind that if you're talking about individual components and how many moles each thing would have, this is something that's helpful. And certainly would be, I think there's one of those questions in this lesson. If you have something like, okay, where's our compound? Barium chloride, right? Where's their BaCl2? The formula weight when you add the components is 208.2. But if you're looking at how many ions versus units, there's a mole of units there, right? 6.02 times 10 to the 23rd pieces of barium chloride. But there's 1 mole of barium ions. How many moles of chloride ions in barium? 2 moles. If I say how many total moles of ions are in the solution of barium chloride? Total of 3. And that's something that's actually kind of interesting. If you think about this idea of road salt. Now in Arizona, I know we don't put salt on our roads because, first of all, we don't have a whole lot of snow. In Flagstaff, when they have snow, they put cinders on the roads. Why do they put cinders on the roads instead of salt in Flagstaff? What's better about cinder versus salt on the roads? Good make chloride. The sodium chloride is iron in one solution. Make a good salt solution. You run it over with iron, that sodium goes up and sticks to the iron. Sodium's wrapped in iron, it gets in place. place where there's oxidation goes on. So that's exactly what happens when the underneath of your car rusts, because the salt catalyzes the oxidation of the iron. Well, in Flagstaff, they put cinders on it. Most of Flagstaff is all volcanic. If you've ever been to Flagstaff, you go to the top of the San Francisco Peaks. If you've never been there, I would highly recommend it. It's absolutely inspirational. You feel pretty darn close to whoever you consider your creator. At the top of the San Francisco Peaks, you can see the Grand Canyon from one side of it. You can see California from the San Francisco Peaks. You look up there, there's all these little mountains, and they're all cinder cones. So what they do is they have a couple cinder cones outside of town, and they go and they get these big dump trucks, and big dump trucks full of cinders, and instead of putting salt on the roads, they put the cinders on the roads. So it's not a chemical reaction, it's lowering the freezing point of the ice. It's a physical change. What's the physical change that the cinders offer that's better for your car than the chemical change itself offers? Traction. Traction of what? Traction, for sure, yes. The cinders are super rough. Cinders don't get smooth like sand or rocks. Like river rocks, you see river rocks are real smooth. Cinders always stay jagged. They never lose their rough edge. So cinders are real good for traction. But what else does cinders do since they're black and you're going to want snow? They have a lot of snow because the black particles of the cinders attract the sunlight, right? The snow is white, and the cinders start to get hot, and they actually start to melt the snow. So it does both. It causes traction, but it also does a physical change. Now, the sodium chloride lowers the freezing point of water, so that's a chemical change. So, let's see, where was I going with this? I know that these pages, I'm going to show you something. Yes?
When did they start doing that?
In Flagstaff?
Or just, is that only in Flagstaff?
It's only Flagstaff because they have almost an unlimited supply of cinders. And the cool thing about the cinders in Flagstaff is at the end of the winter, you know, normally we have salt over the roads, and what happens in other places where the rain comes down and dissolves the salt goes in the soil, it makes the soil very alkaline, and there's something we can called leaching. If you're a gardener like I am, you're trying to dig the ground, and if you don't water your plants very deeply, the leaching makes the soil really hard, and it also changes the chemistry of the plants and makes it hard for the plants to grow. With those cinders on the ground, it doesn't change any of the chemistry of the road or any of that stuff or make the leaching. And at the end of the winter, what they do is they send road sweepers by, and all the cinders on the side of the road, they just sweep them up, package them up, put them in a big dump truck, take them back out to the cinder, dump them, and wait till next week, because they can do them again, because they don't get rough, they don't get swept. They use the cinders over and over and over again, and it doesn't cause your car to be rusted. All right, well, that's all I have for you today. Remember what's happening next week, and to practice on some of these skills over the weekend. Just a second. Let me see if I can figure out how to turn this off. There we go.